If you solve the problem you think is important, that is one definite way to not solve the real problem. You're not solving it for you, you're solving it for other people. So you have to solve the problem that society thinks is important. The funders, the foundations, the government work very hard to define what they think are the most societally relevant things. No process is perfect, but they do a really good job. And so listening and taking that input is also very important. Sustainability is the most conservative possible value. It means that we want to preserve the great things we have and pass them on to future generations. Doing outreach in a way that decreases barriers and increases access to opportunity for anyone who wants it, for anyone who's willing to take advantage, is really important. I really want America to continue to be a leader in science and technology. And in order to do that, we need everyone who wants to be a great scientist, everyone who has scientific potential to contribute to our discoveries, to our technology, to solving our problems.
Welcome to the Science with Impact podcast. Why should our listeners, who the majority seems to be research scientists who want to broaden their societal impacts, why should they listen to our conversation?
Podcasts like yours, they provide a valuable service to the scientific community by getting us to engage not just with the scientific content, but with some of the philosophical meta content. Like, why are you doing what you're doing? Why is it done in this way? People should listen to podcasting and engage in these types of things to stimulate that higher level of engagement with the topic. My name is Brad Olsen. I'm a professor in the Department of Chemical Engineering at MIT. I've been there for about 15 years, since the end of 2009, started 2010.
And how do you know me?
I got to know Vanessa through the NSF CCI, or Center for Chemical Innovation, called MONET, which is run by Steve Craig out of Duke University. I'm a member of that research center, and I'm one of the researchers there. And you, Vanessa, are responsible for a lot of the outreach programs there. And so I think we've collaborated a bit on some of that, and hopefully more of that in the future.
I'm really excited for that potential crypt outreach kit. And I don't know if you saw that Steve and Mike have started to put support behind it and thinking about how do we get the trainees involved in developing it. And so that's the goal for 2026. You know, a lot of the things that we do in science with those outward facing goals of how do we communicate and actually affect broader societal impacts, the big outcomes that we want to pursue is often just inspiring people to envision themselves as scientists and to consider that as a career choice. What was it that allowed you to consider that as a career choice for yourself?
It was actually a family thing. My grandfather was an engineer. I guess I would say I don't consider myself necessarily a scientist. Maybe I am, maybe I'm not. I can't tell yet, but definitely an engineer. And he worked a lot on basically mechanical engineering, did HVAC engineering. And I was definitely less interested in that, but was inspired by the general idea of being able to build things and contribute to society in that way. And I certainly liked science and math as a kid. And I was inspired that was one possible career. Sometimes I think we are at places in our life and we can choose A or B, and we choose A because it sounds good at the time. And that then puts us on a page in the Choose Your Own Adventure book that we didn't quite expect. And we have another A or B choice. We make those choices and you end up where you end up.
I like that idea that we think the choices are infinite, but maybe they're a bit more constrained than we can appreciate sometimes.
The goal sometimes is to find the one everything in life, like the global optimum for our life, the global optimum of happiness, the global optimum of career. And I think my view is life is a little more wandering and a little more random than that.
Tell me more about that. How has that served you, that perspective of life being more wandering and more free than these sort of like A or B binary algorithmic choices?
One thing that's important in science and in life is always be open to new opportunities. Science is changing, especially nowadays, it's changing very rapidly. And if you're still doing the same thing you were doing 10 years ago, that's probably not a good thing. And so being open to those new opportunities, being creative, being spontaneous can all help you to adapt to whatever the future might bring. It can also lead to making mistakes and wrong turns. I think that's a fear a lot of people have. I think If you're willing to drive down a few dead ends, that's probably the price you have to pay in order to be able to explore the really interesting paths as well.
I would love to know, what do you think is the delineation between, this is scientist land and this is engineering land?
I think in reality, there's no clear delineation. I think we refer to things as STEM probably because we couldn't draw nice boundaries around the S, the T, the E, or the M. We put it all together as one big field. People often will say things like scientists focus more on generating fundamental knowledge and engineers focus more on applying that knowledge to solve societal problems. But I know plenty of people who are great scientists who solve societal problems, and I know lots of engineers who generate good fundamental knowledge. There probably is, though, in science, more of an emphasis on fundamental knowledge. And in engineering, there is definitely more of an emphasis on problem solving and application.
Makes sense. The Venn diagram of that is not quite a circle, but there's some overlap. In terms of your outreach work and all the things that you've done as a scientist, is there anything that stands out to you as clearly having enormous potential to reach broader society?
For me, it's very difficult to assess the impact we have ourselves. I think I find we're often biased or blinded and really external input on did that work or did that not work. I guess I would say I feel like I'm the wrong person to ask. And on the impact what we do has, we have to ask the people we're trying to impact and say, how did this work for you? Did this help you? We're not trying to create like a end of the outreach program impact. It's great that everyone's happy at the end of the outreach program. That's probably a necessary but not sufficient condition. But really what we want to see is 5, 10, 15-year long range changes in people's opportunities, in their behavior, right, in society. I haven't been around long enough to have that type of an impact yet.
It's almost impossible to connect a specific event to why someone became a scientist. I have yet to hear a single scientist say it was definitely just this one thing and nothing else mattered. How do you measure that, the impact of your capacity to affect other people?
There are great social scientists who specialize in how to make these measurements. And I just will very bluntly say I am not one of them. We rely on our colleagues in other fields to try to develop better measurement techniques for assessing it. And part of the problem too is that, as we've said, you have to wait a long time to make the measurement, which means that we in engineering call the innovation cycle can be a little bit long. I think that's hard. That's something I struggle with is you want to do it and then get instant feedback. Did it work? And then do it again and then get instant feedback. But I'm not sure that's possible.
Part of my role with Monet is figuring out how do we evaluate our impact and actually measure it. It's one of the hardest challenges is that while we have them there in that moment, I can do a little bit of a pre-post, get close to measuring something like that. But once they leave the venue, I don't have access to them anymore. And it's as though you're creating some sort of change in science and then you just have to let it go. And I don't know, how do you measure that? There's that Harvard study that follows people for a long time and gets to collect data over years and measure their happiness. But we haven't set something like that up yet.
You bring up another good point implicitly there, Vanessa, that I think is really interesting, which is what is our goal? I don't know that there's broad agreement within the scientific community on what the goal should be. Is our goal to increase incomes? Is our goal to just increase the number of scientists? Is our goal to increase people's happiness? Maybe all of the above. Maybe it's not mutually exclusive. I think often with outreach, we'll want to do things like increase the fraction of people who will enroll in college among the participants or something like this. And I think then what's the ultimate goal is something I often struggle with beyond that. Like, where are we trying to get folks?
What's your goal when you're doing outreach?
I think sometimes we just do it for fun because it really is fun to talk about science and share science with people. I think a lot of the students I work with who lead outreach, to be honest, at the end of the day, you can give some official answer, but people do it because they really like it. When you can do things that are good for society and good for you, what a perfect alignment of interest. I really believe in having a society where everyone has opportunity. And I think that for us, doing outreach in a way that decreases barriers and increases access to opportunity for anyone who wants it, for anyone who's willing to take advantage, is really important. Thinking of it from a nationalistic perspective, I really want America to continue to be a leader in science and technology. And in order to do that, we need everyone who wants to be a great scientist, everyone who has scientific potential to contribute to our discoveries, to our technology, to solving our problems. You don't take a sports team and bench half your athletes, not let them practice. Everyone gets involved, everyone trains, everyone contributes. So I think that's a key goal for us, is trying to get broad engagement so that we can have as many talented people as possible having opportunity.
One thing that I really admire about your work is you definitely want to affect change within the United States, but you don't limit yourself to that. How did your experience as a Fulbright Amazonian scholar shape your approach to outreach, particularly in Brazil?
It's very humbling starting to do international outreach work. The perspective we have on ourselves within the United States is not necessarily shared by people in other countries. So I think you really have to do a lot of learning and a lot of listening and understand where people are at in different places and what their different life situations are, what their backgrounds are, what their views on different world, historical, cultural events, trends are. To give you one kind of fun example, Ford Motor Company actually had a major business in the Amazon making rubber for tires. And there's, of course, a long history of the rubber industry and its relationship with local and indigenous people, its relationship with basically rubber tappers, extractors, unions in this region. That's a very powerful history and very important history. I think most people in the US aren't aware of that. They show up in the region, and I think there's a high risk that we can make mistakes basically because of our lack of awareness of what's happened. So I think learning is really important, learning about people's perspectives, doing a lot of listening. You don't want to take this view that sometimes we do, where you're the expert and you just got off the plane and you're going to tell everyone else how to solve their problems. What a short-sighted perspective on things. You have to look at it as collaboration, right? I wouldn't go over to my neighbor's house and tell them what to do. So when you go visit your neighbor's house, you're a guest. Of course, we collaborate with our neighbors. We support our neighbors. We build strong communities. And I think the same way I would interact with my neighbor, I hope that we as a nation, as a society, will interact with our neighbor society in order to build strong relationships, build collaborations, develop solutions to our common problems.
Did your experience with Fulbright help you become more aware of those perspectives that can be damaging in those relationship building initiatives with neighboring countries?
I think it helps you become aware of many things. Having a chance to interact with other scientists from many countries, having a chance to meet a lot of different people and a lot of community members in different communities and cities throughout the region was very powerful. It was also a ton of fun to have a chance to meet and interact with diplomats from many different countries. I found that very enjoyable as a scientist, seeing how this kind of messy, chaotic turn of science was getting translated, in a sense, into official positions or at least statements from different government agencies.
Why Brazil, just out of curiosity?
For a long time, my kids went to daycare at MIT's daycare, so I had to drive them in every day. And the daycare opens at 8. There's no way to avoid rush hour. So I was driving right during rush hour to and from work, and my average speed in the traffic in the Boston area was about 10 kilometers per hour. And so that's miserable. And I have to go 10 kilometers. I found I was arriving at work really angry, and then I was like, I need something to distract me in the car so that I can just stay calm. I'm going to learn foreign languages on tape. So, like most people in America, I was going to do Spanish. So I started doing Spanish. And I worked on that for 6 months. And then the problem I had was that nobody wanted to practice Spanish with me because I was pretty bad. So, like, there were a bunch of Spanish speakers around. They're like, dude, don't speak Spanish to us. At that time, I had a couple colleagues who were Portuguese speakers through the MIT Portugal program, through a Brazilian postdoc who was visiting, and they were super supportive because I would say not so many people want to study Portuguese in the US. So it's a rarer event, right? So they're like, you should switch to Portuguese because look, we speak Portuguese and we'll help you. I was like, great, I'll just switch to Portuguese. And I did, and they helped me, and it really got over the hill in terms of developing language skills. And that just opened so many different doors for collaboration in Brazil. Yeah, I'm always so excited to go interact with my Brazilian colleagues. It's always fantastic. Feels like a second home at this point.
I'm so curious about what makes people fall in love with learning. And it seems clear to me that your first solution to resolving the anger that results from a stressful commute was how can I make this productive, learning, and fun? I think that's such an interesting because you could have listened to anything. You could have decided that's going to be the time that I just listen to music with the kids. You chose to learn a language. And that so clearly has had ripple effects throughout your career that you may not have had if you didn't have that stressful commute. So there's just so many aspects of that. Is there anything else that you would love to comment on?
I just don't understand why people don't like learning stuff. I guess I get that learning is hard, but isn't doing new stuff fun? You probably can't learn the advanced science we do off of YouTube, but you can definitely learn a lot of stuff. I think that's a great way for people to stay fresh and stay young at heart, if not what the calendar says, right? I know they say your brain is supposed to become more difficult to learn things with age, but that's why not keep trying? Because it can bring you joy, just the joy of learning something, no denying that. But how about the joy of being able to do something, like having a new skill? It unlocks doors, lets you solve your own problems, lets you be independent, lets you feel actualized as an individual. I think that's great. I think we should give more people the chance to just teach themselves stuff. I see things where people talk about feeling unempowered or feeling trapped. How can we give you a skill that will allow you to untrap yourself?
I've met a handful of people in my life, and I'll admit it's rare because most of the people that I get to spend time with love learning. That's my favorite question to ask people I've just met. What are you learning now? And I will meet some people who go, I'm not learning anything. I'm not reading anything. I'm just getting through the day. And I wonder if the other side to a love for learning is just comfort with discomfort of failing, the comfort with not knowing something. I'd love to know your perspective on that. Are you comfortable with failure? Do you think that has a big part of your willingness to learn?
I think everyone's probably on a spectrum. I don't like failing at things. I don't like screwing up. Most people strongly prefer winning. I would definitely put myself in that boat too. I think characteristics that drive quest for learning are people with short attention spans, bored easily. But I think often when you're like, I already know how to do that, therefore it's less interesting. Those types of attitudes, I think, push people. What don't I know how to do? What's more interesting? I think also more of that explorer ethos correlates highly with this frontier person ethos. That sort of ethos, which is very strong in US traditional culture, right? This is something I think that ties in very heavily with lifelong learning. And it inspires me that during that frontier, that sort of ethos and culture drove a lot of American innovation in public education and increasing education. And I think education is breaking down frontiers. Your individual frontiers are being broken down as you're educated. It's whatever way you can find to get in touch with that kind of primal piece of being a person.
I think what makes a lifelong learner is that they don't view it as failure when they don't know something. It's an adventure.
I think that's right. Viewing failure as a piece of the adventure. It's not the fun piece of the adventure.
That is so cool and interesting to think about the way we perceive challenges in life. If we perceive it as an adventure, if we perceive it as, I'm not 100% successful at executing this thing I don't know yet, so I don't want to do it anymore.
So much of what we do involves things in this vein. And I think one key piece is that things like risk and adventure are fun up to a certain level of risk. And then beyond that, it becomes anxiety inducing, stressful. So it's really hard to take risks, go on adventures if you're hungry. And if there are serious security issues or safety issues, it's really hard to take risks and go on adventures. At the same time, we want to encourage risk taking and individual accomplishment, breaking down barriers, exploring, which is inherently a little less uncertain. We have to give a solid foundation, both in our own lives and to all our innovators in science and technology, so that they have the confidence to be able to go on those adventures.
If you don't have food security, the only adventure you're really concerned with is securing that and ensuring that like for our students in particular, if our students are housing insecure, food insecure, learning probably isn't in their top 5 priorities right now. It needs to be in our top 5 priorities to make sure that they have that so that they can learn. You've been instrumental in developing interesting data tools. PolyDat is a great example for the data tools that you've developed in polymer chemistry. What has motivated you to focus on things like this, like data sharing and standardization in polymer chemistry?
I think tons of people in the scientific community share this goal that we would like to see scientific community make a transition from a fairly labor intensive enterprise to an enterprise that really uses the best of automation, machine learning, and these new trends in order to accelerate discoveries. I think this has some huge benefits for us, especially in light of some of the societal challenges that we're facing. Just to name a couple, so this transition would have the potential to dramatically accelerate economic growth, which I think it's always a win when we can raise people's standards of living. This type of transition could potentially help to address the fact that we have an aging society. And so we're going to have fewer young people coming into science relative to the size of our population in the upcoming years. This is a real need. There's not going to be the ability to drive scientific progress with youthful hands. And so we're going to need some of these things. I also think that being able to make this transition successfully is very important for our national competitiveness and our security, being able to continue to be leaders in these areas. And so for all these reasons, we want to see this transition happen. As we looked around in our own tiny corner of the scientific universe in polymer science, what we saw was a transition about 8 or 9 years ago now. The trend actually this was catalyzed. I should include one piece of story I can leave out though. During the Obama administration, they started a big program, the Materials Genome Initiative. And the idea was to catalyze transitions like this. I think the vision has matured since then, but I think this was a really big foundational government program trying to get this started. I was lucky enough with another MONET investigator, Jeremiah Johnson, to have one of the first awards as a part of this program. And I went to the meetings with the other people in the program, and then we realized right away that our field was 2 decades behind the other fields in the program. And it was to the point of being disturbing of how far behind we were. That really got us thinking, like, what is it that can do this? And we started learning about different things that were going on in these other fields. And I just got really inspired. They can do this. Why can't we do this? And that got us to thinking of how we could, in fact, solve that problem and do some of those things. And a lot of those things fundamentally relied on being able to address issues with data and the way you could share data, the way you could standardize data, the way you could compare data. I think the basic premise here is that no one person can generate enough data to make these modern labs go. So you need lots of people. If those people can't effectively share and collaborate, then you're sunk, right? Everyone's always starting from near zero and trying to grow. And you can't grow effectively that way. You have to be able to build on one another and work together. So I think a lot of these tools are trying to accomplish that. They're trying to bring people together in a collaborative way to allow them to work faster and make this leap to kind of what we see as the modern lab.
For those listeners that we have who may not understand the unique challenges of communicating polymer chemistry, could you explain that?
So a couple of years ago, we celebrated the 100th anniversary of polymer science. The day that they mark is like the birth of polymer science was the publication of a paper saying that polymers exist. And the idea or the debate 100 years ago was that how could you have a molecule so big? The other side of this is that polymers don't even have a single unique molecular structure. And being able to accept the fact that you have these molecules that are very big, that are stochastic in nature, that are actually mixtures of many molecules with different molecular structures, that was recognized with the Nobel Prize. So that was a big change in people's paradigm. And the problem that I think we saw was that no one had yet made that paradigm change in chem informatics. Everyone was still stuck on every molecule must have one unique identifier. That identifier is a single molecular structure, and the tools were all based around those assumptions. Those assumptions work very well for many branches of chemistry. They don't work well for materials, for polymer science, for supramolecular chemistry, for colloidal chemistry. And so we said, look, let's take this thing we know now to be very well true, and let's see if we can build it into chem informatics. Basically, build that change of assumption into chem informatics. And I think that was the key realization and motivator to make the advances.
Why don't those assumptions work for macromolecular structures on the polymer scale?
Each polymer is a mixture of different molecules. The mixture has something in common. So, for example, if I say like polyethylene in like your laundry detergent bottle, more than likely your laundry detergent is packaged in a polyethylene bottle. So, it's a high density polyethylene to be particular. So, this bottle is made of many polymer molecules, all co-crystallized together. Each molecule has a different length, right? It has a different number of ethylene monomers that were put together into that polyethylene. This gives you a molar mass distribution. The ways of representing molecules at the time we started principally focused around writing a structure that had a defined molar mass. But the polymer doesn't have one molecule with a specific molar mass. And so that made capturing all that diversity challenging. When you go to more complicated polymers, you can have, for example, sequences with different chemical groups in different orders. You can have stereochemical variability in addition to the molar mass variability. Sometimes you do just have blends of multiple components beyond just the molar mass variation. We have variations in branching and topology. So instead of being a straight line, the chain can have side branches off of it. Those side branches are at different locations of different lengths. The branches can have branches. And so all of this produces a lot of randomness that had to be captured and that wasn't effectively captured before.
How does one create a data tool that can even get close to capturing that nuance?
We can tell you what we did, but that's this n=1 argument for innovation and creativity. It's saying if you just do exactly what we did, then you'll get a new creative solution. But I would say, since we already did that thing and made that solution, by definition, you can't do what we did ever again. It worked to produce that thing. So I don't know what the process is. I think it goes back to some of the stuff we were at the beginning, being open to changes in direction. I mean, why we'd never done informatics before. Why would we start? But we saw this thing, we're like, oh, this is pretty interesting and it's obviously important, and why not work on it? One of the things I do my best to emphasize to my researchers is that I think the most important thing is to want to learn, to be really hardworking, and to really put your talents to use. And if you do that, then it doesn't matter if you know a skill right away or if a barrier comes up. I have a lot of confidence that people who are hardworking, who put their talents to use, and who are willing to dig in and learn new things, they'll get around the barrier. This is historically a very proven recipe for success. So I think we have some people like that, or we had some people like that who jumped in on this problem. We're just like, wow, this looks really creative. Yes, we're inspired that the general outlines of a solution exist. We can see a light at the end of the tunnel that we think we could get to. We have no idea what's between our dark feet and that light, but they're willing to take the leap.
Like you said, an N of one, it won't get you to the same result, likely. But I would love to know more about how you started to progress from so much nuance in the structure of a polymer. How do we create a data tool that can help researchers not have to start at ground zero? I'd love to know just even how you began to tackle that problem.
A lot of engineers learn formal design processes, and one of the things they tell you at first is you really need to know what problem you're solving, and you need to invest a lot of time in making sure you are, in fact, not only solving the right problem, but you're doing something that will, in fact, solve the problem. A ton of time has to be put into understanding the contours of exactly what you're trying to solve. So here, pretty quickly, we understood, okay, the problem we are trying to solve is going from a deterministic representation to essentially a stochastic representation. And to rephrase that, what we decided needed to be done, what we thought was a viable solution, was to, instead of writing a single molecule structure, to write a notation that represented a set of molecules. And so then we thought it was going to be likely possible, and I think we were right, to be able to write the set notation in a way that it would represent every molecule consistent with the chemistry that was done. So far, we haven't gotten any counterexamples, so I'll assert until proven wrong that could still happen, but I'll assert till proven wrong that this concept seems to be general and that we can represent all the different polymers using a carefully crafted set notation. And that's really what was built. And yeah, the realization and the place to start was being like, okay, how will you capture this stochasticity? We'll capture it by writing sets. And that properly defined the scientific problem, which was the stochasticity, and it properly defined a feasible solution, even though there's no details in what I just said. So you got to work out all the details. Working out all the details took 2 years. Deciding that the problem was viable and coming up with a prospective solution probably took a month. But getting the right problem definition and the right viable concept solution early on are very important.
This might be an oversimplification, but would you say that the data tools that you and your colleagues developed could be analogous to the way mathematicians went from using actual numbers to moving to algebra and allowing variables to represent numbers?
Probably not as impactful as that one, but it was a change in the fundamental conceptualization of the problem. I think many scientific discoveries are. If you read a scientific paper and you read the beginning and then you're like, oh, I know what's going to happen. And then you read the results and you're like, yup, that's exactly what I thought. That's less interesting than if you read the beginning and you're like, I think this is going to happen. And then you're, whoa, that is not what happened. And then they explain to you why. And you're like, oh, I learned. Because that goes back to that's the act of learning, right? Because if I think something is going to happen and I'm right, I didn't learn anything. If I think something's going to happen and I'm wrong, then someone taught me something. So tapping into that desire for discovery and learning, fundamentally, discovery and learning at some level has to be unexpected, new, shifting the mode of our thinking.
Wow, I love that. It took me to when I was in general chemistry as an undergrad, and I was trying to wrap my head around stoichiometry. There was no amount of exercises and calculation that I could do to understand it conceptually, and I wanted to understand it so badly until I discovered that there is an example out there where, open to the environment, the mass of the products is more than the mass of the reactants. And I was like, that doesn't make sense because of the law of mass conservation. And it wasn't till I understood, oh, it's an open system. So it's attracting, bringing in oxygen atoms and binding it. And in that process, of course, because we're bringing in from the surroundings, the mass is increasing. And that's where that comes from. It wasn't until then that I understood, oh, this whole chemical reaction thing is a process. You start with all the reactants and none of the product, and then it becomes, as the reaction progresses, now you have more product. I didn't understand that one fundamental piece, even all the way in undergraduate chemistry after taking AP chemistry in high school. I didn't understand that because I had put it all into these math equations. This idea of it's not until you're confronted with something that you didn't expect that you get the opportunity to learn. That's where that took me.
One of the challenges I think with that, at least just speaking for myself, we so quickly forget what we didn't know.
Yeah, absolutely. Do you mean that particularly as an educator?
You can't imagine what it's like not to know those things. I have this problem all the time. Of course, everyone knows this, right? Because I've known this for 5 years, but that's such a obvious fallacy, and it's such a difficult fallacy to shake.
That makes sense. I think sometimes the worst students make the best teachers because of that. They can remember not knowing. They can remember what was the breakthrough that they had that helped it make sense. Could you tell me, we're thinking about this outreach kit and bringing crypt into it and how we can maybe even integrate this idea that we're talking about where students might expect or participants might expect it to go a certain way and then we'll surprise them with something else. That to the development of the outreach kit with crypt, but could you help me expand on that?
My goal with the outreach kit is a little more mundane, and I think it's motivated by identifying a problem. So I think there's a problem in education that we haven't moved digital tools up to an early enough stage fast enough. My kids do everything at school on a Chromebook. So it's not like there's not a computer, but the digital tools they're using are pretty much YouTube and word processor. So it's not really the level I'd like to see, right? I'd like to see the integration of coding. I'd like to see the integration of informatics. I think all this should happen at an earlier stage. Like, why can't kids, for example, code things in Scratch in middle school and use them in their science class? I don't know. But this is a specific area. I think with these science kits, I think one of the key goals here is to address the issue of bringing chem informatics to a much earlier stage. So in the chemistry space, we basically use hieroglyphic to write our chemical structures, but we draw pictures, right? And from a very early stage in chemistry, we all get very good at it. My hypothesis is, and I would view that as a language, right? It's a pictographical language that we use to communicate our chemistry. I would say we all get good at it, not because it's a superior language, but it's because it's the one we're taught first. So I think one of the goals with these hits is to see if we can start moving towards a way of making our students bilingual in chemistry, where they can speak in the pictographs, but they can also speak the informatic language from a very early stage. I think if we do that, what we're going to do is we're going to be empowering all students, not just the ones who move on to super advanced education, to participate in the new innovation economy, which is going to be driven by these tools. So to broaden that participation, to provide opportunity to increase the pace of innovation, we got to get everyone trained up in how to do these things.
So I just recently started a collaboration with the University of Florida's pharmaceutical chemistry department. And what they've tasked me to doing is very similar to what you're describing, teaching these medicinal chemists using Lewis dot structures. So like the stick figure representation of chemistry. And they were telling us like the biggest challenge we have is getting them to understand that these molecules exist in 3 dimensions. Because when you can't picture the activation sites and like the different where the proteins can bind to the receptors, it makes it extremely difficult to understand how these molecules happen in the body, particularly when you're just using that reduced 2-dimensional stick figure. So my task is to go in and animate in 3D what is occurring here and allow the students there to interact with these in 3D. So would you say that would make it trilingual for the students? Because now we have the stick figures, we have the informatics, and then we have the 3-dimensional representation?
Software at recognizing drawn images and converting them into standardized chemical structure data formats has started to get pretty good. I'd say it doesn't exist yet for polymers. We're trying to build it in collaboration with Connor Cawley's group at MIT, but it exists for small molecules and it's pretty good. So I wonder if we're not too far away from a day when things like you're doing will become an app on a student's cell phone. And what they can do is when the professor's lecturing, they'll just point it at the board and it'll scan in like Google Translate the picture, and then it'll generate a 3D image that they can turn and spin and visualize in real time, because the professor's never going to draw that on the board. And let's also be real, professors move away from chalk at a glacial pace. This is like the pace at which dinosaurs evolved. We love our chalk. Partly that's a good thing because PowerPoint education is not necessarily a win. I think the chalk may actually not be so bad, but the ability to take what is representable within a lecture, which is very limited due to time and due to the speed with which information can be conveyed in an oral format, and being able to enrich that in real time visually, I think this is something that's super possible. So you should build that.
Avogadro, the app, does a really great job of you draw it and you can do like an energy approximate where it'll go in and calculate what is the lowest energy for this molecule. It's pretty close to what this might look like. We're so close to having all the pieces. It's just how do you write the language needed to take it from now we're scanning it much like a QR code and it takes you over here. Yeah, we're almost there, right? Speaking about like your work, it spans all of these very diverse sectors. So we've got like health, sustainability, national defense. How do you decide which societal challenges you want to tackle? You mentioned as an engineer, defining the contours of the problem you're trying to solve is very important. How do you decide that? And then how do you go about communicating that to your stakeholders?
Yeah, I'd say it's a convergence of two factors. I think science exists in a sense in a market. So we have ideas of what we want to work on, what's important, how to solve problems. And then the people who support science have ideas of what they want to support, which problems they think are important, and which approaches they think are going to be valid. And of course, they have proposal review processes or grant selection processes for helping to make those determinations. And they have committees of very wise people helping them to decide, right? And so these two sides meet in a market, right? Where the scientists are pushing ideas and the people who are ready to support science are defining what they think is important. And the key is finding that intersection where the things that you feel like you have skills that you can do, that you're confident you can approach, you have a good idea of how to solve the problem, overlap with where the demand is. And of course the demand is always changing, right? The demand changes with world events, it changes with the political temperature of society, what people think is important and what we want to work on. And part of it, of course, is pushing things forward, and part of it is listening and being responsive to what society wants. As scientists, you don't, again, back to problem definition, as you said, if you solve the problem you think is important, I would say that is one definite way to not solve the real problem. Because you're not solving it for you, you're solving it for other people. So you have to solve the problem that society thinks is important. And certainly the funders, the foundations, the government work very hard to define what they think are the most societally relevant things. No process is perfect, but they do a really good job. And so listening and taking that input is also very important.
It's really interesting to not focus on the problem that you think is important, but to listen. We keep coming back to this theme of the importance of listening.
You should, of course, also listen to yourself and what you think. The primacy of your opinion over the opinion of everyone else is a danger.
Maybe it's a pretty easy trap that we can fall into as scientists, especially a scientist like yourself who's winning a lot of awards and just a notable standout, I think, in the science community. It can be easy for that to over validate our opinions over others. And I really appreciate the humility through which you approach these issues. How do you navigate the balance between these are the efforts we're doing to advance the science or solve the problem, and these are the efforts that we're taking to communicate it and share it with other people beyond academia? How do you navigate balancing those two, what I think are very different actions in science?
For better or for worse, our primary responsibility is in the former. Mostly we are engaged in order to solve the problem. And then less are we engaged in order to communicate it. I don't know what the right balance is, but I do know the balance is very much weighted in favor of the former. Maybe it's not as asymmetrically weighted as it would at first appear because the communicating is very much across multiple constituencies. I think we often think of the communicating as being communicating to society as a whole. And in that sense, it really isn't a large fraction of time. But if you think of, well, communicating to industry, communicating and advising the government, sharing with colleagues or undergrads versus graduate students versus professional colleagues, then when you add up all the different constituencies, I'd actually say the time spent communicating science is huge. It maybe even crosses to be almost equal to the doing the science. But I think the traditional definition of communicating out to society as a whole becomes a small piece of the pie, whereas these other, and no one of these constituencies is huge, but when you add up all the different constituencies, I think it adds up to quite a bit. And I think there's a lot of value there. Communicating to broad society is extremely important, but industry needs special communication at a different level to be effective. They don't need the general societal communication. I think that benefits them, but they need communication targeted to their business needs, their industry, by helping them to take decisions, to make investments, to identify technologies, to address liabilities. And so this, of course, is another specialized form of communication that we often don't recognize, but I think is extremely important to this broader impact of economic growth and competitiveness. As you've already highlighted, the undergrad education and graduate education are a core piece of what we do. That's 100% communicating science. So yeah, add all those things up. I think the balance is very much in favor of majority of time is spent communicating. But Each constituency occupies a narrower slice.
What I'm hearing is a reflection on what we were talking about earlier. Knowing what problem you're solving seems to, it should maybe heavily weight the consideration of who you're solving the problem for and what problem they perceive you're solving. When you're communicating, it seems similar. Knowing what value you're communicating and what the person who's receiving it gains, know your audience in a way. Problem are you solving in communicating the science to an undergraduate in your class and shaping the communication around that value, that solution? I don't know, am I getting close to that theme?
I think that's absolutely right. Knowing your audience is key, and our time is divided between many audiences.
Is there a science organization or a cause that you would love to take a moment to just highlight?
I've always been very passionate about environmental organizations, and there are so many great ones that focus on conservation. But I think, especially living in New England, we largely settled this piece of the United States before the national park system and before some of the other real focus on land conservation. So I think some of the efforts going on in state to preserve a certain fraction of the state's land by certain dates. So there's these 30 by 30 pledges and things like this for land conservation. Some of the work of land trusts, the work of wildlife federations, work of the Nature Conservancy, all this stuff gets me really passionate. It ties in with sustainability, right? I think fundamentally to me, sustainability is the most conservative possible value because it means that we want to preserve the great things we have and pass them on to future generations. That's really something worth investing in. And so I love all the work that those different organizations do.
Every episode, we ask the guest prior to leave a question for our next guest. Last was Paul Ferron. So he is a materials engineer also, and he's working on this incredible podcast called Incredipol. He asked, I'm curious, if you were not this prestigious scientist at MIT, what would you be doing and why? And he gave some context because he thinks there's always a different version of ourselves where the intersections of who we are could have gone in one direction or another. And he's curious about your path and what that might have been.
I agree with him. I guess the question is, what's the premise? Like, how far from science do I have to go? I think at various times I've thought it would be super fun to be a winemaker, run a vineyard and make wine. I thought it would be fun to be a scuba instructor, although I quickly disabused myself of that notion. That's really hard work. It looks cool while you're young, but that's hard work. Maybe like living on a vineyard in like upstate New York with my fields of Riesling. That sounds lovely, but you can tell that's purely fantasy without any actual connection to reality there.
I think for a lot of people, the idea of being a prestigious researcher at MIT, it sounds like pure fantasy. So I think it's okay to dream about that sort of thing. I love asking people this because I've heard everything from I would be a yoga studio owner. Surprisingly, a lot of scientists will say an analogous career. Instead of being a chemist, I would have been into computational chemistry. Like they'd shift just disciplines a tiny little bit. But I think it's really interesting to hear yours.
It's definitely the career I have is a great career. Thing that I most miss is the opportunity to be outside more and to be in touch with nature more. And so career where I got to be involved in outdoors or agriculture or something like that sounds very appealing on the days when you're stuck in a fluorescently lit building all day.
You got asked a challenging question about you and your career and your future. And so I'd love to give you the opportunity to ask a challenging question to our next guest. What to leave for them?
What's her view on what we can do to get scientists into sort of societal leadership slash celebrity position? It's interesting because I think a lot of scientists mock the concept of science celebrities. Right? Oh, you're not a real scientist, which is probably untrue. But yeah, asking what she sees about the value. Could that have value? Is it a good idea? How do we encourage more scientists to become civic leaders?
Thank you so much for spending your very valuable time with me today and just giving me the most wonderful conversations. This is such a great way to start the day on a high note.
It's been a pleasure.